Aquillone is an individual research organization based in Japan. We focus on the theory of everything. Also, we create fascinating ideas to accelerate the technological growth of Type 1 civilization. We are creating favorable conditions for the human society to enter the next stage of evolution. In all our videos, you can find some interestingly new ideas. Inflationary epoch. In this video, we are going to describe what happened in the inflationary epoch and the reasons for all these things to happen. First, we will check the situation of the Big Bang Singularity and its surroundings at that particular moment of the Big Bang. Afterwards, we will discuss the inflationary epoch. We will finally try to find out how everything that happened after the Big Bang is happening in a different way in our daily activities also. Because the universe has only one law. Even if it is a Big Bang or if we throw a stone into the atmosphere, it will work under the same rule. First, we will check how the universe was before the Big Bang. Here we can consider the universe as a combination of two different systems. A system with fully concentrated matter and another system of space-time. Some people may say that there was no time before the Big Bang. That also we can discuss here. The Big Bang singularity was not created in just a moment. It took billions of years to store this much energy into the singularity. So there must be a time before the Big Bang also. You can find a detailed explanation on this subject in our other video. Was there a time before the Big Bang? Or you can visit our website for more information. If you wish to know the complete history of the universe from the beginning stage of the singularity, you can read our book Key to the Secrets of the Universe. There we are explaining the universe from the primordial collision of two particles to form as a singularity. I will add the link in the descriptions. The singularity was still gathering energy or matter at the moment of the Big Bang. As it adds a particle to the singularity, some proportion of spacetime also will be added to the associated spacetime of the singularity. So while growing the singularity, the associated spacetime also will grow with it. The primordial universe that mixes primordial particles and spacetime. Here the distribution of particles in spacetime creates an imbalance. But if we distinguish only one particle, it is said to be in equilibrium. Similarly, if we consider a space-time without the presence of the particle, it is also said to be in equilibrium. The primordial universe was unbalanced in conjunction with two phenomena like energy and space-time, but which are in equilibrium when they are separated. The same thing happened in the Big Bang singularity also. There were many favorable conditions for the Big Bang to happen. This is also one of its reasons. The particles and space-time were separated from each other and tried to create an equilibrium. We can already see many reasons which can break the equilibrium of the singularity. First, the pressure inside it, and then the curvature that it creates in the space-time where it exists. By increasing curvature, singularity can also compress the space-time more. In addition to this, as the amount of energy within the singularity increases, an imbalance between energy and space-time increases. You can see a complete structure of how matter is accommodating in the space-time in our another video, the unification theory. There we are unifying all the fundamental dimensions like mass, time and length in a single scale. You can see a mathematical description of unification of dimensions in that video. I will add it to the end screen. Now we can back to our singularity. A normal black hole singularity may not bend space-time in such a terrible state. But when we talk about the Big Bang singularity, we have to think about this because it had the energy to create the entire universe. It would have bent space-time in a way more horrible than we thought. The reaction of space-time against it is perhaps the underlying cause of the Big Bang. Maybe the gravitationally curved space-time also needs the Big Bang to happen. As far as I understand, space-time is very flexible. Energy can use space-time as it pleases. When energy expels all the space inside it and enters into a singularity, the space-time around it is more likely to shrink. As the concentration of matter in an area increases, the characteristics of the space-time over there also undergo some changes. Space-time around the Big Bang singularity must have been very much compressed. It was with such a force that the energy within the singularity pulled the space-time into it. The flexibility of space-time also changes according to the pressure exerted by the energy on the space-time. The movement and the speed of the objects moving through it will also change according to the flexibility of the space-time. We have proved experimentally that light bends under the influence of gravity. The space-time within the event horizon of a singularity must be compressed very much. That is why even light cannot escape from there. Anyhow, with the help of a picture, we can try to understand more. This image is what I drew from my imagination in a way that everyone could understand. The horribly curved space-time. The red spherical part of the figure indicates the Big Bang Singularity. The grey colored top side shows its even horizon, and the black curved lines represents the terribly curved space-time. In a picture representing a singularity, we usually see a cone-shaped curved space-time. But things are a little more complicated here. Curved space-time is merged together for some distance. After that, its curve slowly appears. In fact, a spherical singularity creates a curvature of space-time from all sides. When you try to fold space-time with such a force, naturally there creates an imbalance. There was such a powerful activity because of that much energy was involved in that region. There is another point to consider. Does the singularity occur only in one place in the universe? We can never be clear about this. We have not been able to understand the boundaries of the universe or its vastness. Let us just say that the universe is infinite. We cannot tell how much energy the whole universe had. But in future, we may calculate how much energy have in our universe where we live. Because our universe was formed from a singularity that stored at exactly the finite amount of energy. We have talked about the circumstances surrounding the Big Bang up to now. Now let us see what happened after the Big Bang. With the Big Bang, our universe has to change its state into an expanding universe from its previous state of a singularity. When switching from one condition to another, the first thing it tries to do is to maintain the stability. But we have three different scenarios here at the same time. First, the singularity continues to store energy until the moment of the Big Bang. Second, the state of singularity that has existed since that moment has ceased. Finally, the universe is starting to expand. At the same time, the singularity breaks down and the Big Bang occurs, and the energy flows into the space-time. At this condition, space-time also goes through three different situations in a similar way. As each particle is added to the singularity, the space-time also increases proportionally. Loss of stability of space-time. Finally, space-time collapses down and penetrates into the singularity. At the very last moment, one particle dissolves into the singularity and many other particles are approaching to the singularity. This was the scenery at the time of the Big Bang. The Big Bang was never an explosion. It was a breakdown of two equilibrium states of interaction. Space-time and the singularity are undergoing some changes at the same time. Both are simultaneous processes. This is an ongoing phenomenon. As the universe expands into space-time, changes will also occur in space-time which is covered by its gravitational field. The scattered matter after the Big Bang will create curves in different places in the collapsed space-time. Here we can try to view the universe as two basic forms, energy and space-time. Energy with the help of its own gravity causes changes on space-time and expands into it. The universe is a mix of functional reactions between energy and space-time. Space-time is also trying to survive the changes created by the energy in it. Anyhow, things happen from 0 to 10 raised to minus 43 seconds after the Big Bang are still unknown to us. But I will try to explain the situations of that period. 10 raised to minus 43 seconds is a shorter time than we can imagine. Think that if you wrote 43 zeros before 1, how small this is. In physics, such a short period of time, we call it Planck time. Hence, the period from the Big Bang to this time is called Planck age. So we can assume that Big Bang happened at 0th second. The new time which begins with the Big Bang will be added to the space-time. A new space-time will be created there. The new space-time must have been created along with the Big Bang. Otherwise, there will be a time difference between the space-time and the Big Bang. For example, suppose time is added to the space after the Planck age, then there will be a big difference between the timeline of Big Bang and the timeline of space-time. Right away with the Big Bang, the situation already existed there is changing. The energy stored as a singularity is released. A massive disorder in the curved space-time by the singularity will happen. The energy from the singularity will start to spread in the space-time. In this case, both systems will attempt to regain the lost equilibrium. The distracted singularity of the Big Bang and the space-time destroyed by the Big Bang will prepare each other. Singularity is said to exert its energy into space-time, and space-time will prepare to accommodate it in. This kind of preparation must have been done during the Planck age. For that, the Big Bang singularity will be releasing a massive temperature. Space-time will absorb it. This will cause the temperature of the universe to be decreased. As we know it today, the four fundamental forces that we know in the universe appeared together during this period. At the end of the Planck age, gravitational interaction disassociated from the electronuclear interactions that have held it together. Gravity stays part of the energy and the other fundamental interactions become free. The inflation era then begins as a result of these preparations. We can realize that inflation has an important role in the expansion of the universe. Even in every action of our daily life, we can relate inflation or the Big Bang. After the Big Bang, we can see that there is an acceleration occurring in the expansion of the universe. The expansion of the universe in this stage was at an accelerating rate much faster than the speed of light. The inflationary epoch started 10 raised to minus 33 seconds after the Big Bang. This may have lasted up to 10 raised to minus 32 seconds. During this period, space-time which joined together in the Planck era began to penetrate into the distracted singularity with a massive velocity. At the same time, the energy released by the Big Bang began to penetrate rapidly into the shattered space-time. Both of these things happened at the same time. We can describe this as an interaction between energy and space-time. Here we see space-time and energy acting as motivating forces to each other. Space-time inspires energy to penetrate into it. Similarly, energy invites space-time to penetrate into it. This is the reason for the tremendous acceleration of cosmic expansion during the inflationary period. In my opinion, physics is a true understanding of the characteristics of the universe. The nature around us provides all the answers to its phenomenon if we look at it carefully. Inflation made me think a lot about the Big Bang, the force created by the Big Bang, and the after effects of the Big Bang. It causes me to think deeply about what we do in our daily lives. I understand that we can keep track on inflation in every activity that applies force. In my logic, inflation is an effect which is created by an external force when it is affecting on an object or another force. We can view it in all actions. For example, if I am throwing a ball at a velocity of 10 meters per second and it will still continue its motion at the same velocity. We can ignore the gravity for a better explanation here. It is obvious here that before I threw the ball, it was at an inertial stage. Its initial speed was 0. When I put a force on the ball, it quickly reaches the velocity of 10 meters per second. We can observe the inflation here. The time taken to reach the real speed using an uncontrollable acceleration. The force I applied to an object was capable of delivering the speed of 10 meters per second. Inflation is the initial acceleration of an inertial object when it suddenly moves. This fraction of a second we can say as the inflationary period of that force. In this period, the object will get an acceleration at a very high rate according to the amount of applied force. Here is another example to explain the inflation. Here we can observe a billiards ball. When the ball hits another ball, the kinetic energy shifts from it to the other ball. I ignore all the other balls on the board for a better view. So the second ball is gaining momentum in it. The influence of the external force will fulfill all the parts of the ball uniformly and abruptly. This will be a driving force for it to move. Because of this, it gains a sudden acceleration and we call it inflation. And the speed of this uniform filling of the force to the object will depend upon the strength of the force. If the applied force is weak, it will affect the body slowly. The force that was created there during the Big Bang was beyond anything that we can imagine. We can see that this will be a lot more influential in its later journey. Now suppose we are applying a force on an object traveling in a straight line. The trajectory of the object also changes depending on the force we are applying. Depending on the nature of the force we are applying, it may increase or decrease the velocity of the object. Relating all these things with the phenomena which occurred in the time of the Big Bang is more challenging. But we have to do such a correlation because the universe has only one law. Whatever things happen anywhere in the universe must have to be explained in a similar way. Even if it is the Big Bang that triggered the cosmic evolution or any small action we do, it will all happen under the same rule. We are just experiencing these in a different manner. There were many developments during these periods during Big Bang. We can never experience all that in the small activities we do. For example, during the Big Bang, massive amount of energy are emitted and fundamental forces are freed. None of this will appear in our small actions. This is because of the strong force created there and then by the nature of the singularity. But there may be something similar happening in our actions. There is much more to be learned about it. Let us return to our billiards board. When a ball hits the other ball, we can observe some kind of vibration on the ball and it will make a sound too. We can say that it is a reflection of the force we applied. At this point, the ball will make an effort to stabilize its state of being. At the same moment, the force applied to it is evenly distributed throughout all its parts. We can compare this period to the Planck age. Almost all of these two things have been happened in the Big Bang singularity and in the curved space-time where it exists. Once the force is evenly distributed, the next phase begins. Thus, they are preparing to accommodate the changes. On the one hand, the singularity is preparing to spread to the space-time from the state of unity. Same moment, the space-time covered by the strong gravitational field is preparing to absorb the sudden changes. The phenomenon of the Big Bang breaks the state of singularity. So does the state of space-time also. Once an equal amount of force is distributed, the other fundamental forces within the singularity can be freed. At the same time, to avoid the disturbance within it, the damaged spacetime will apply a strong force to the shattered singularity. This period in the Big Bang was marked as the grand unification era. The next phase of the inflation era begins as the continuation of these events. Here energy can enter space-time very quickly. One advantage of this phase is space-time applying a force over the singularity. Likewise, space-time prepares to absorb the energy into it. This causes a sudden acceleration of expansion of the universe. If we take a closer look at these periods, we can describe the universe in more detail. Even the separation of the basic forces each other in different stages. I think you get the idea better. Thank you for watching.